very special, strange phenomena that appear in the galactic center. Well, he's now professor at Northwestern University. He worked at Columbia University for his PhD, and then make a 2 years postdoc at NASA Goddard Space Flight Center. And he joined then the Department of Astrophysics and Physics in Northwestern in 1988. So in the 100th parsec of the galactic center, you know that there are very strange phenomena. There is not only a supermassive black hole, of course, but also dense particle clouds where you have formation and huge magnetic field where they are preventing a big disturbance. And then yesterday, Farhad told us about the filaments. There were 1,000 filaments that he observed with Meerkat. And today he will speak about the flaring activity, which is a near infrared and X-ray. You have flares every day, and the rotation of the gas around is about quarter of an hour period. So he will speak about that.
Okay, merci beaucoup. Thank you so much for having me today. It's really wonderful to be back here a second day. I hope you're not sick of me by the time you leave today. So I am excited to tell you a little bit about the work that we've done recently on the Galactic Center using James Webb Space Telescope. And so just strictly talking about the black hole at the center. And this work was actually published a couple of months ago in AppJ. So if you really want to see more details, you can look at that paper. And also, we're working on some continuation of this work. If I have some time, I can tell you a little bit more about them, preliminary results of some of the work that we're doing currently. So this is a cast of characters that are involved in this project. Many of them are my longtime collaborators. We worked together for decades, but also a graduate student, Joe Mikkel, who finished his degree, and he's now at Center for Astrophysics at Harvard. So what am I going to be talking about today? Just give you I know that there are not many people who work on the galaxy here, so I just give you quite a bit of introduction as to why we study this region, why is it exciting to really learn about this part of the galaxy, and then talk about James Webb telescope observations, and then if I have time, I can talk about infrared flaring activities and how they relate to also radio and submillimeter and perhaps even X-rays, if I have time. And then I wrap it up at the end. So just put everybody on the same page. I want to just show this little video. We are about 8 kiloparsecs away from the center of the galaxy, 25,000 light years or so. So this is a sort of a quick journey through the center of the galaxy, and you can just see for yourself that optical image of the galactic center is pretty obscured completely. See all these clouds, and then of course all the stars that you see are foreground stars, because background stars are completely obscured. You have 30 magnitudes of extinction due to clouds, interstellar clouds. And then now I'm making a transition to infrared. Infrared, the magnitude extinction is about 1/10 of optical, so 3 magnitudes of extinction. You see the crowding now that is happening in stars, cluster of stars basically approaching the galactic center. And then you have to use adaptive optics. So now we're going from basically 2 mass data, and now we're going into adaptive optics that can individually see stars, and then all of a sudden you see stars are moving, whipping around like crazy, and that's really the famous S2 star that I'll talk about in a little bit. So it's really quite, so this is orbiting around the black hole, and that's what we're going to be talking about today. So let me step back and show you again an optical image of the galactic center. And of course, the radio image is really, technology was developed much earlier than other wavelength bands. And you can see that how radio image along the galactic plane shows all kinds of interstellar processes, interstellar clouds. And it's a sort of really an extreme environment of the galactic center. The inner sort of few hundred parsecs of the galaxy, and the black hole here is right at the center here. And so just I think I talked to you with you yesterday, just show you what this image is, that this interesting region of the galaxy also shows these unusual synchrotron filaments that we talked about yesterday. So it is an interesting region of the galaxy with lots of unusual phenomena happening in this part of the galaxy. So now let me zoom to the inner few light years of the galaxy, where there is a molecular cloud that is orbiting around Sgr A star, shows up in red. It's about 100 kilometers per second orbiting, and then the ionized gas, mini spiral sometimes called, it's an ionized gas that is also orbiting around the black hole itself, Sgr A star. And Sgr A star really shows up here at radio wavelength. It's one of the brightest sources in the sky at radio wavelength. And this source was actually discovered originally in 1974 by Malik and Brown. And you can see this is only a 3-element interferometer with all kinds of side beams, side lobes that are showing up here. But what people have learned from measuring the sort of the kinematics of the gas in this towards the inner few light years of the galaxy was that there is a massive object at the center of the galaxy, and this massive object was known to be about a few million solar masses. The problem was that in the 70s and 80s, people couldn't really find the compactness of it. So it was sort of there was a mass there, but it wasn't clear exactly how to pinpoint exactly where the central object is. So it was not very compact. And then, of course, that led to a lot of ideas about that there is actually a cluster of stars. There could be a cluster of neutron stars, a cluster of white dwarfs. It could be, so there was all kinds of ideas those days, 70s and 80s, and even 90s, that there's maybe a cluster of stars at the center of the galaxy. And those days, people really didn't talk about black holes the way we talk about black holes these days. So just the people, they were very regarded and reserved about using the idea of a black hole at the center of the galaxy. And so that's a bit of a history about the just what we knew about in the 70s and 80s from observing the gas in the galactic center. But then infrared technology and infrared imaging really changed the entire picture of the galactic center. And now you can see that there's a cluster of stars. There's a nuclear cluster centered on the galactic center. And then on top of this, coexisting with another cluster of massive stars. There are about 100 to 200 of these massive OB Wolf-Rayet stars that are orbiting around the center of the galaxy. And these are all sort of powerful mass-losing stars. Their winds is basically up to about 10 to the minus 3 to 10 to the minus 4 solar masses per year. And they all coexist within an evolved cluster which is over 1 billion years old. So that's actually one of the interesting things, is that nobody had expected to see these massive stars being formed so close to the center of the galaxy. And not only that, but it's also formed within a disk. So in 2 disks, but 1 disk is very prominent, showing up here, a clockwise disk that these massive stars orbiting around Sgr A star. And so when the extinction is low, you can do quite a bit. So let me merge now into just a simple old diagram that these stars, these OB stars, are moving around the center with the red vector, and then there's also the blue stars that are a little bit further away, and they're not as clean as the disk stars associated with these massive stars. As you can see, the velocities of these guys are pretty well known, and so this was really an unusual discovery, that why you get these massive stars forming in a disk. How do you actually form stars near a supermassive black hole? Nobody had predicted, because everybody thought that, well, forbidden. tidal forces really dominate, you wouldn't expect to see massive stars forming so close to a supermassive black hole. But in fact, nature does produce this, but there are some ideas we still don't understand, and but just to give you a sort of a simple picture that we had a while back. So you need to have obviously a gaseous disk around the supermassive black hole in order to fragment it and produce these massive stars that we see, Wolf-Rayet massive stars going around the black hole. And so the question is that how do you get this gaseous disk so close to the black hole? And you can see this is only a light year sort of accretion of, well, sort of star-forming clouds that fragmentation happens and forms stars. So one idea that we had was that perhaps a cloud a few million years ago, an inhomogeneous cloud, as you can see here, molecular clouds, these giant molecular clouds, you see a bunch of them actually towards the galactic center, just runs basically radially in the direction towards the black hole. So as it basically goes around the black hole, you basically have a situation where the gas gets gravitationally focused by the black hole, very strong 4 million solar mass black hole here. So the gas basically collision happens on the other side, and you lose a lot of angular momentum as a result of the collision from both sides of the cloud. So as a result, the gas that is basically carved out from the passage of a molecular cloud stays with the black hole, because the black hole has a sort of a capture radius that it basically captures the gas. And since the gas is now losing a lot of its angular momentum, then it basically gets brought in closer to the black hole. So you start out with about maybe 3 parsecs. So this is where the capture radius is, but then lots of angular momentum actually brings into the gas to about 0.3 parsecs. And there you have this diagram showing that what the disk would have looked like. And so what happens is that as long as the shear time scale for star formation for the gas is much longer than the dynamical time scale, then you have a fragmentation happen and stars can form. And we think this regime can actually form massive stars. And then a good fraction of the gas is also in the innermost part of the disk. And this could, in fact, be accreted onto the black hole while star formation is taking place. So the idea is that since now the shear time scale is much shorter here, then you can't really, self-gravity cannot really dominate in this regime. So the gas can actually fall into the hole. And if it does, then you can have a situation where you can get an enhanced accretion, and there is sufficient mass in this regime that can actually produce even the Fermi bubble about 10 to the 55 ergs. So just to give you context here, about a couple of 100,000 solar masses of gas need to be producing the 200 solar massive stars in the galactic center in this region. And then you have the same amount also within the closer to the black hole here. And this should be basically, if this picture is correct, should go into the hole. So it's a very interesting situation that you can have both a starburst happening at the center several million years ago, but at the same time, you could have an enhanced accretion and producing an outburst, for example, perhaps producing also the Fermi bubble. So this is basically one way. The idea is one way that you can actually bring in the gas and then starts, in order to really produce massive stars in a disk, you really have to have a gaseous disk. And it's been always an issue that how do you do that? How do you bring in the gas so close to the black hole in a disk-shaped structure? So this is one way to do that. So now let me step back again and zoom in closer in to the inner arc seconds of the galaxy. And these are what is known as S-cluster stars. These are also massive, they're B-type stars. And this video actually shows the motion of stars as they orbit around the black hole, very well known. I mean, it's a remarkable sort of series of measurements that are done over decades. It's not just the S star, all of these stars, the orbital parameters are recognized, and you can get so much information out of these stars. All of these data are available, and you can actually download them and try to play whatever you like to do with them. But here, the most interesting source or star is S2 star. And these, we don't even need general relativity. You just basically use Newtonian physics, and you can measure the mass of the object because now you're so close to the black hole. And so that's what the two groups had done. The two groups, one at NPI in Germany and the other one at UCLA, they were really a number of things happened for this major discovery was that adaptive optics was invented first. So they could really see things a lot clearer, so close to the galactic center. They were also observing for decades. So that really gave them an edge. And the third thing was that S2 was also another source that nobody had predicted to have so close to the black hole. So really there was a series of things, just being lucky and also technology really helped them to really put together a remarkable measurement that led them to get Nobel Prize from Nobel Committee, Reinhard Genzel and Andrea Ghez, the fourth woman who actually has won a Nobel Prize. So the two instruments that they used was the Keck telescope and also the VLT, and that is actually now into an interferometer that I'll show some of the results. So the mass is now measured very well, accurately. Now the next step was that VLTI was used. VLTI is sort of interferometer, infrared interferometer. The VLT actually was able to actually see the motion of S2 star. And one of the things that they discovered was clearly the gravitational redshift. So sort of Newtonian motion, basically, you would expect to see be along this dotted line or dashed line here, but they saw S2 star actually really going up by about 200 kilometers per second, redshifted right around where the pericenter, as it orbits around the black hole when the velocities are highest. So all the other velocity components are taken out, so you can see clear indication of gravitational redshift. Another thing that they discovered was that the S2 star is actually precesses. Similar to Mercury is going around the sun, except that it's much larger, about 12 arc minutes per orbit. This is again, these are predictions of general theory relativity. And another thing that they tested was the equivalent principle, because they were able to actually see hydrogen and helium lines, and they couldn't see any difference between the two. And they set an upper limit of about 100th or so. So this is good enough, but you can do, certainly they can do better measurements in the future for the equivalent principle test. Another thing that they discovered was basically the relativistic time delay. And this is showing, this is Sgr A star, and this is the orbit of S2 star. And you can see the accuracy at which they can actually measure the position or the astrometry of S2 star. So it's such an incredible resolution that they have. Astrometric measurements is about something like 3 milliarc seconds. And this is, the accuracy that they have is only 1 day. So in other words, you can see May 24th, it's basically the accuracy is between 24 and 25, or 23 to 24. So it's only 1 day. This is really remarkable. We're talking about a source that is 8 kiloparsecs away from us, and we know the position of the source within a day. When we come back 2 days later, we know that it's actually moved as a result of a passage right around the pericenter. So that also is sort of tested the relativistic time delay, and of course, so you have all these predictions of general theory of relativity, and they all checks. Obviously, you know, Einstein was right, and Another series of measurements came from radio side, and that is a picture of what you've seen before. So what I've said so far was really general theory relativity was tested at a much larger radii, not under a strong gravity. They were still under sort of a 0.1 light year or so. So if I actually remember what that is, actually the scales that we're talking about less than it's certainly a few month light travel time. But here now we're talking about the strong gravity. We're getting into within a few Schwarszchild radii of the black hole, and what you see is it's really a result of a shadow of black hole is showing up, and that happens when you have a black hole and you shine light from the backside of the black hole. Basically, as it passes through, it sort of forbids a small radius, and all the radiation basically just passes, and we can observe it except within a few gravitational radius. A gravitational radius is about half of Schwarzschild radius, it's 1/2 of Schwarzschild radius. So it's basically, that's the region that where you see a dip in the radiation, but then the photon ring shows up, resulting from this idea that how the radiation gets focused by the black hole. And so this is actually quite remarkable also. This is really the evidence that we have a supermassive black hole at the center of the galaxy. And of course, this is about 100 years after Einstein presented his theory of general relativity to the Prussian Academy of Sciences. And so it's really wonderful to really celebrate this achievement that was done by the EHT. But also I want to tell you that this is not totally correct. These blobs that you see certainly need to be sort of studied in more detail with better data. And of course, this is not something I'm saying for, it's new, but it is known, the uncertainty in terms of and that is all because of the variability of Sgr A that is creating some artifacts in the shape of the ring that we see at the galactic center. So radio really started out in 1974 with a sort of a 10-centimeter wavelength with a resolution of a few arcseconds or so, 3-element interferometry. And now in 2017, you have millimeter wavelength radiation coming from the black hole at a resolution of a 5 microarcsecond. That's also just a remarkable achievement also in the radio part of the spectrum, that how much, again, we're really standing on the sort of shoulders of technology. And that's what this image is telling you. Very wonderful result that was done. And we now know, so we can study basically what the structure of the black hole, the Schwarzschild size scale. Now, you may ask the question, well, what about the accretion disk? Where is the accretion disk coming from of the black hole? So there is now consensus that the material that really feeds the black hole here, so this is the innermost part of the accretion flow, but the outer accretion disk basically goes up to about 10 to the 5 Schwarzschild radii. And we think that this gas is coming from mass-losing stars that are orbiting around Sgr star, and the winds basically from these massive stars collide with each other, and a fraction of it gets basically just fed into the black hole, forming an accretion disk. So this is what people have been thinking about, and people have done all kinds of simulations, and so let me just show you one very wonderful simulations done by Ressler and collaborators. What they did is they knew the orbits of all stars, these massive stars that I mentioned before, Wolf-Rayet and OB stars. They knew the mass loss from individual massive stars, and then they put in the simulations here the winds and also the bubble that is created and shock gas here And then, so they did it in two steps. First, they basically ran the simulations, by initial conditions. You have these massive stars already, and the gas collides with each other, it produces X-ray gas, and a fraction of the gas goes into the hole and producing an accretion disk. So once they did this part, formed an accretion disk, then they went in a second series of simulations to follow how the gas basically gets into the hole and accretes onto Sgr A. So I'm going to show you just these simulations, see it for yourself. So you can see the angular momentum is different for these guys. And of course, there is a lot of variability expected because each of these stars have different orbital time scale. The orbits are very different, so they collide with each other. And you can see there's one little tiny bit structure here that you show. This is where Sgr A is located. This blob is actually where the accretion disk is. So the gas, a very small fraction of this ionized wind, X-ray emitting ionized wind, gets into the hole itself, passing through the captured radius of the black hole or Bondi radius of the black hole, and that's what this is. So they were able to really find out what fraction of this mass loss from stars go into the hole. It turns out that you start about 10 to the minus 3 to 10 to the minus 4 solar mass per year from these stars. And it turns out that it's only about 10 to the minus 8 to 10 to the minus 9 solar mass per year basically gets accreted, gets basically fed into the accretion disk. So you can see how poor, the efficiency is extremely low because it's X-ray gas. They're all flying in every direction, but only the coolest component of the gas basically gets feeds into the accretion disk of the black hole. And then what they did, once they figured out how much matter goes into the hole, then they started basically doing in other simulations, much more detailed simulations of the inner arc seconds. So this is the accretion disk. The gas is basically has a magnetic field, and it's there's all kinds of physical processes basically that the gas gets, and you can see there's a lot of variability is happening in this as the gas gets closer and closer, and also the magnetic field piles up as you get closer to the black hole. So you have basically gas pressure and magnetic pressure are all basically coming together closer and closer, and of course they're not equal to each other. And then at some places, basically, as it gets closer to the hole, so this is an accretion disk now that we're talking about. And then as it gets closer to the hole, every now and then, the magnetic pressure basically is so high that it actually erupts from the disk itself. And this is something that I'll talk a little bit more about. These eruptions are really what we think is the flaring activity that we see towards Sgr A. And there's a lot of interesting physics involved here in terms of compressional heating, for example, and how the gas gets closer in. And so it's quite, and then they were able to really figure out what fraction of the gas gets into the black hole and what fraction of it gets basically blown up as an eruption in this region. So hopefully I can tell you a little bit about it. This is basically a density simulations of the gas as it gets closer to the hole. Okay, so now that we have a situation where there is a gas coming in from these mass-losing stars, and some fraction of it, just 10 to the minus 9 solar mass per year, it's really very low density gas. It's really unique region of the galaxy, I mean in the universe actually. You have an accretion disk that is basically peaking at sub-millimeter wavelength. This is a SCD of the black hole itself, peaking at about sub-millimeter wavelength, and it is incredibly powerful variable at the radio and X-rays, and it's mainly synchrotron radiation here. The gas that I showed you earlier, these are all Bremsstrahlung radiation, thermal Bremsstrahlung, but then they become relativistic Maxwellian distribution as you get closer to the hole itself. So we think that these are all synchrotron radiation in a relativistic Maxwellian distribution that is producing the, so this is As you can see, there's a lot of variability here at higher frequencies. And that's what we're excited to study, to learn about so the efficiency is very low, as you can see, 10 to the minus solar 9 solar mass per year. But also, since the density of gas is so low here, then you don't have a lot of collisions between electrons and protons. So what happens is that electrons and protons collision time scale is much longer than the cooling time scale. So as a result, electrons and protons are going to have two different populations. Electrons basically don't get any energy from protons, and they basically, there's not much radiation coming from the black hole accretion disk. Just simply, that's another efficiency, lack of efficiency. One is the fact that you don't get a lot of material coming into the hole. The other thing is that you have this sort of a two temperature effect, temperature of gas, protons, and the temperature of electrons. And electrons don't get any energy out of protons because they don't collide enough. As a result, they don't radiate. So they just basically advect into the hole itself. So these are two issues related to black holes that are dormant when the density of the gas is fairly low. One last major discovery that was done by the VLTI is that they were able to actually track the flaring activity around the black hole. So what you really see here is that flares are showing up, and at near infrared, they were able to actually see that it's relatively orbiting around the black hole. And this is only about a few Schwarszchild radii. So now we can have a fantastic situation where the variability is probing accretion processes within strong gravity. The innermost region of the black hole accretion disk is now flaring, and that's why we're excited to study this part of the galaxy, because this part of the accretion disk, because it's really, there's a lot of interesting physics involved by studying the variability of the accretion disk itself here. And this is what I'm going to be talking about. And we were excited to study this with James Webb, the Space Telescope. But before I actually get on to the variability, let's see if there are any questions, anything that is not clear. Or maybe you want to wait until the end. Okay. Anyways, just sometimes good to take a break, because there's a lot to take in. I hear you. I know there are lots of graduate students. You guys do cosmology, so it can be overwhelming. But now I'm going to just talk to you about tell you. Yes, question.
Sure. What's the orientation of the accretion disk of the line of sight?
It's actually tilted quite a bit with respect to the galactic plane. So there are two different disks, but the two disks are actually. Oh, are you talking about the disk of the stars or the accretion disk itself?
Either and both.
Oh, okay. The accretion disk itself, we don't really know for sure, but we think that it's a little bit sort of inclined by about 120 degrees. So it's not exactly 90, but it's not. So it's a little bit. So that's what the modeling has been done. Yes.
And when you talk about the different temperature for electrons and protons,
Yes.
what is roughly the temperature for them, and also the flares are in which wavelengths, in infrared or in X-ray?
Yeah. So just the latter question I'm going to be talking about now. And electrons and protons have two different. There are many different models of this that has been done. Honestly, don't know what the temperature is, but it's very different from each other. And this is really assuming that you have Maxwellian distribution of particles in the disk, but it doesn't have to be. It could be a power law distribution. People have done this as well. So it's sort of model dependent, but I think it's something that this two temperature distribution of the accretion disk has been used now in other galaxies when there's not, the efficiency is very low. Okay, so now I'm going to talk about the James Webb data and what we learned from observing the galactic center flaring activity. And of course, you all know that the JWST is about 1 billion miles away from us, and that has fantastic advantages because you can observe it for about 24 hours straight with no problem. Whereas you could not do that with Hubble or any other telescope. So it's really, really nice. You can do, and so this is a list of people, and one of my collaborators is actually among one of them. I don't know where he is, but this Rick Rand from Goddard Space Flight Center is in here, and this is a mock-up of the telescope that was sent to space. So why did we really need to study this? The main reason was that there are two instruments observing simultaneously, and that is something that has not been done before. It's really remarkable when you have two instruments observing at 2.1 and 4.8 micron, and that is really just the simultaneity changes everything, because then you know the spectral evolution of the flaring activities. And so that's one advantage, and there are of course other advantages. You have a 6.5 meter telescope, you have basically so far away from us, and so it's really sort of nice to observe this with James Webb Telescope. But there are also caveats involved here. You can see that this is an image of at 2.1 micron. You can see all the dark features are saturated stars. It's a very confusing region, and of course it took us some time to figure out exactly how to observe. And this is one thing you don't want to do when you dither. There's no dithering. Don't do dithering when you observe it, especially with the galactic center, because you lose your guide star. That's one of the problems that we've had. And now we actually stare at one position for a long time. So we learned our lesson the hard way. So just show you some variability that we see from Sgr A star that we observed for 48 hours spread out over 7 epochs. And you can see 2.1 micron and 4.8 micron here shows up, and you can see the light curves of the stars nearby, reference stars, very close to Sgr A star. It's really incredibly flat, no variations whatsoever. And so every little fluctuations that you see here is real. And so there's no, is always varying the galactic center accretion distance of the black hole. We observed, in fact, these observations, we had at least 2 epochs with the EHT, the event horizon observations, but there usually it takes a long time for them to analyze the EHT data. So hopefully we can actually put these together using basically the imaging and also the variability, help them out to get a better image of the galactic center accretion disk. Just show you also the just for a single day, you can see there are lots of variable flaring events that you see. Flares are the ones that really are bright, that you can see several times during the day. And then you also see these low-level fluctuations. And low-level fluctuations are also, even when you have a flaring event, it's always sort of showing up. It's constant. We have not seen a situation where the fluctuations, the low-level fluctuations stop. And flaring happens quite often. I want to also point out that each data point here is about 18 seconds. So you can see that how all of a sudden the Sgr A star becomes brighter. You can determine that it's actually varying on a time scale of about a minute. A minute time scale. The orbital time scale of the black hole at a Schwarszchild radius is about a minute. So really, because the mass of a black hole is so small, you only have 4 million solar mass black hole. So the orbital time scale is going to be about a minute. Whereas when you have something like a M87 or 2,000 times more massive than the sun, this size scale and the time scale is going to be very different than what you see a small black hole. So these are some of the advantages that you have on a short time scale variability, just simply because the mass of the black hole is small. And so that's what we see that. We may be able to see this, but you have to pay 2,000 times more time on other nearby galaxies.
You mean this is the time at the ISCO?
It's outside the disco. The flaring is happening outside
But
disco.
the period is at the,
The period of disco is about 30 minutes or so.
you assume no spin for the black hole.
So far, I haven't done analysis, but we assume, yes, for this step. This is something that we don't know. It's a holy grail of the galactic center black hole is that what is this spin? How is it really moving in terms of its spin? And that's something that will come, I think, in the future, I hope. So yeah, you can see there are lots of really interesting sort of fluctuations. What is it? It's very stochastic. It all makes sense because when I showed you this accretion disk as it orbits close to the center, you see all kinds of variability. There are lots of things going on a short time scale. And this all really is fed by the mass losing stars that are basically feeding the accretion disk. And then the variability is actually imprinted on these light curves. So it's really interesting that how this whole thing, the process, how basically stochastic processes basically feeds into the accretion disk, and then you actually see these eruptions as a result of being fed by stellar wind sources outside the inner arcsecond of Zadeh star. Okay, so we got these light curves. So, well, what have you learned? It's all nice. So I'm just going to tell you a little bit about what are the things that we learned from these light curves. It's flares and flickers, the power spectrum. These are a few things that you can do. So you have these light curves, beautiful, but what do you do with it next? So I'm going to just show you a little bit about the analysis of this data. So first thing we did is just looking at the histogram. It's very simple. Look at the histogram at 2.1 micron fluxes, basically flux histograms, and also at 4.8 micron. And you can see the sort of the flickering events, low-level fluxes are here, the brighter ones are here. And the same thing that you can see, so this suggests that you have two different populations of particles producing the emission. The emission that we see is synchrotron. It's an optically thin synchrotron emission produced as a result of the variability all throughout, from the fluctuations to the flaring events. So it's all synchrotron emission that we see. So that suggests that you have two different populations. It's not, you can't fit the two together with one log normal or one power law or what. So that's something interesting to note. Another thing that we did is said, okay, why don't we just look at the fluxes at 4.8 micron versus 2.1 micron and see what we see. And a really fantastic result came out of this. Just a simple idea that you basically, flux versus flux, showed that the slope of the low fluxes, low flickering events, basically have a different slope than the ones that are showing up at brighter fluxes. So this is only 1 day of observation, but we had 7 days, and they all show up like this. So what is this telling you? This is the flare that I'm talking about. This analysis, the colors are all matching these colors here. And so what we do is the spectral index of the fluctuations, low-level fluctuations, is actually steeper than the bright ones. And that is interesting. There's always been a controversy among different groups, especially UCLA and MPI, that what is going on with the spectral index. This spectral index is really, for some of you who are not familiar, it tells you about the energy index of the particles that are radiating synchrotron radiation. And so this tells you that these are steep and this is flat spectrum clearly. Without any other analysis, you can see that it's actually just changing the switching at about 3 millijanskis at 2.1 micron. Another thing that we learned was, so the idea is that you have two population of particles producing low-level fluctuations and bright flaring events. So that's what this implies. Another thing we did was the power spectrum of the radiation that is coming from the variable source. And you see that it's a power law index for 2.1 and 4.8 micron. So there's a wide range of time scale. So it's a power law index. So it's really, Sgr is varying really on a long list of the continuous sort of variable emission on different time scales. These are the time scales variability. This is the frequency variability. And then you get on a longer time scale at about 7 or 8 hours, then it becomes more like a white spectrum, white noise, essentially. Not that it's noise really, but it is. So you can think of it more like the black hole is constantly bubbling with emission, very close on a smaller scale. And then when you look at the accretion disk on a long time scale, on a large scale, then you see the flow is going slowly up and down. So that has a sort of, that's what this implies. And this one is the inner part where the variable emission is happening at a short time scale, and this continues on to sub-minute time scale. So it's really fantastic. You're getting into really a regime that is the size scale is about a Schwarszchild radii in the accretion disk of the black hole. So you're probing something interesting. Flaring is telling you something about the sort of the physics of the accretion flow very close to the black hole. Another interesting result that came out of this was to look at the spectrum of the radiation for flares. So this is a typical simple flare. So you see these also fluctuations. They're always there. So flares basically rise and then it decay. On a time scale, which is roughly about maybe 20 minutes or so, 20, 30 minutes or so, for a simple one, rather than multiple flares. And if you look at the spectral index, you see that's the thing, the beauty of having a telescope that has two different instruments simultaneously observed, then you can see the spectral evolution of the different parts of this, this flare. So you can see that in the rising part of the spectral index is actually shallower than the falling part of the spectrum, where the spectral index is actually steeper. So you do see a slight change between this part versus this part. You can see the same picture here. So in other words, you get a loop diagram. And these loop diagrams are quite telling because you can actually model it and learn something about the magnetic field and electron densities and all that. So this, we think, is due to the fact that the 2.1 micron fluxes, the particles that produce 2.1 micron fluxes, these are basically power law distribution of particles. They basically radiate faster than particles that produce 4.8 micron due to synchrotron cooling. So synchrotron cooling has a time scale which depends on the wavelength. So for example, if you have a magnetic field of 30 Gauss, the synchrotron cooling is about 14 minutes at 4.8 micron, but at 9 minutes at 2.1 micron. So essentially, so you get a mismatch between these two different wavelengths, and that's what the spectral index is actually telling you. And you can model this by saying that, okay, so I have a distribution of particles, electrons, power law distribution of particles, and relativistic particles with some energy cutoff, and I just let that go, and then follow basically the evolution of these electrons as they radiate, and due to synchrotron cooling, and then you find basically compute what the population looks like. At the end, as a result, you can actually model this with this simple picture, toy model, and you can get some. So these are basically what we see observing the flares, and this is where the loop diagram is. The brown line shows the model, and from this modeling, you can actually learn a few interesting things about the black hole flaring events. That the magnetic field is fairly strong. You get 90 to whatever 70 Gausses. You learn that the electron density is about 10 to the 4 to 10 to the 5 particle per centimeter cube. And you may say, well, what about the size? And these are all the minimum size. with respect to the gravitational radius, since this is optically thin emission, optically thin synchrotron emission doesn't allow you to measure the size. Optically thick emission can. So we have just only the minimum size of the flaring event. So you learn something interesting about the sort of physical characteristics of flaring events, and so that could be very interesting also. Another support for the picture of the synchrotron cooling is that you have the cross correlation between 2.1 and 4.8 micron, and you can see a time delay. So in other words, 2.1 micron fluxes come first, and then 4.8 micron fluxes peak later. And this is what it's saying, 40 seconds, and this is 25 seconds. You see it throughout in all observations. So this is, I want to point out that this is really remarkable because no one has actually seen the time delay between two different wavelengths, because we never had that opportunity to observe with such a great sensitivity and being able to really pinpoint basically a time delay between them. And this is just due to synchrotron cooling time scale that we see this mismatch, a time delay. So it's consistent with the picture that I mentioned before, that how you can actually generate this kind of a synchrotron cooling seems to be pretty reasonable from this observational standpoint as well. So, so the million-dollar question is that how do you produce the flaring event? So I talked a lot about the physical properties and what we learned. And people have studied flares for 20 years with ground-based telescopes. We're learning something new. And now many simulations have really converged into the idea that the variability of Sgr A is due to the rupture of the gas very close to the hole due to a strong magnetic field. And this is what is happening here, is that the gas, basically the footprint, when the magnetic field becomes strong enough, the pressure of the magnetic field becomes strong enough because the magnetic field just piles up. As the gas gets closer to the hole, it piles up. As it piles up, eventually it reaches to a point where it's greater than the gas pressure, and then you have the foot points of the magnetic field, and you can also have rotation, shear happening, and of course you can actually have magnetic field basically rubbing against each other and produce a reconnection of the field lines, and this reconnection of the field lines produces an acceleration. The acceleration of the particles that are generated as a result of this rupture then produces a plasmoid that is basically ejected off of the disk. So this is sort of a picture that multiple simulations are indicating, and we think that these measurements that we have is consistent with it. So let me show you this simulations again. Hopefully I can now go. Yeah, that's the problem. I can't really fast forward, look, because if I fast forward, then you see that how a rupture happens. You can see some of these blobs are being ejected from the center in green. But as you get close to towards the end of this video, you really see beautiful sort of plasmoids ejected off of the black hole. But these are basically snapshots. Even actually, this one may be actually telling you something. So this shows the density, temperature, and the flux magnetization. So this is showing you that how the gas, some of the gas that is basically ejected, these balloon-shaped structures are ejected, and this is really telling you quite a bit, because now the magnetic field in the z direction is dominating, and then the gas basically gets ejected, gets ruptured, and they follow basically how it goes in the direction of away from the accretion disk of the black hole. And what's interesting is that when you look at the light curves, the accretion rate decreases as you erupt material, because some part of the disk is now ejected, and as a result, the accretion is lower going into the hole. So that's what this is telling you, is that both the ejections, and there's a correlation between the gas accreting onto the black hole and also ejected material from the disk itself. This is a snapshot in other simulations, and it shows the same idea that the gas basically, this is now showing in different times, and you can see towards the end, you can see these blobs that are ejected. This is showing you the temperature, I believe. Now, this is the density. The densities, you can see the densities looking, it's a sort of a hollow structure, and you can see also the temperature, I believe, here. Yeah, this is the temperature, and this is also telling you what beta is. Beta is the ratio of the gas pressure to the magnetic pressure. And so beta, when it's low, you have a very strong magnetic field and the rupture is happening. So you can actually learn from these simulations, quite interesting. And we think that what we really see, the flaring that we see associated with these ruptures are actually are observable at near infrared. And so how much time do I have?
1 minute?
I have 1 minute. Okay, so anyways, I want to get into radio and submillimeter. That's a different, but it's very related also. Radio and submillimeter shows the same picture that you have a material ejected off of the disk. And this is something that we actually had results like 20 years ago, believe it or not. But these new simulations are really putting a lot of life into these measurements. So let me wrap up and just summarize what I've been talking about. I think the variability of JWST is really over time, wide range of time scales from minutes to days to months. Every time you observe over 2 years, it was something different. It's non-stop activity and low-level activity, obviously. We see time delay and loops in the spectral index versus flux, telling us about the cooling time scale of electrons. And we think that there are two different processes producing flares. Flares are, we think, is due to ejection of material off of the disk. Flickers, not known. We don't know exactly how these flickers are generated. Could be turbulent heating, for example, producing them. It's something certainly to think about in the future as to what is the role of this flickering emission that we see. It's certainly synchrotron, but they're different than flares, so we don't really know how they're generated and how they. So plasmoids due to reconnection. It's really a lot to really also study. This is not all close sort of book here. The reconnection of field lines and the spectrum. This is all a good idea. I think it's, but you need to know whether you can actually accelerate particles to GeV electrons due to reconnection of field lines. What kind of spectrum would you expect to see? And these are not done yet. So there's a lot of work done, need to be done theoretically to see if this reconnection idea actually works and is consistent with observation. And as I said, the flickers, and I didn't get a chance to talk about this, some of the future challenges for us, obviously, I start with this one. The spin of the black hole is really not known. Hopefully one day we have a better image of EHT combined with flaring can actually tell us about the whether we have measured the spin of the black hole. Another thing that we don't know is that whether there's a jet coming from JWST. All simulations that I showed you indicates that you would expect to see a jet coming off from the black hole, but has not been seen yet. Partly, I think, observational details, we don't have such a high resolution image to show that. And of course, it's really important to do this kind of analysis year after year and see how the black hole is really changing. Every time we observe, the black hole showed something interesting. And we just perhaps learn something about the history of the black hole over a long time scale. I think that's all I can say. Thank you very much.
It's wonderful talk. The question.
Thanks very much for the lovely talk. So You didn't actually say very much details about your JWST observation. Is it near cam or what is it?
Yeah, near cam.
You didn't show any images.
I showed one image.
So you must have spatially resolved information in those images.
Honestly, EHT, sorry, the VLTI, images are much better.
That's why you don't show them.
Well, it was just moving out the black hole. We don't really see the accretion disk, we don't see any of that stuff. These are all really realm of EHT in the future.
Okay.
But yeah, but it's the images are a lot of saturations, but this is more, it's a different project we're doing also about star formation near the black hole. There, we really need imaging to see what's going on around the black
The
hole.
thing you're most interested in the fact you have the simultaneous observations.
Yeah, the most interesting is that we have two different wavelength observations, and that's what the variability component is telling us quite a bit about. The accretion process is very close to the inner disk of the black hole.
Yes.
You have a continuing program?
Yeah, it's a long story. Unfortunately, we had 2 years in a row, and then we got turned down because what I really like to see is 24 hours straight. And it's a lot for 24 hours to give to the committee. So we're hoping to do a DDT, this is director's discretionary time. And so we're hoping to do something like that, and maybe next year we'll observe again. So we have only 2 years. Hopefully we can do something more along the way.
Two questions.
What does the prospects of detecting neutron stars or white noise near the galaxy star?
Neutron star. Well, there is a pulsar very close to the black hole. It's about less than another second, and people are studying it in the radio and trying to really see the orbits and how it's going. There's a lot of work in this area of just pulsar search very close to the black hole. And there's I think Meerkat is going to play a big role also. They are spending about, I think, 100 hours only on Sgr star to really see if they can detect the pulsar very close, because then you really probe something completely different, and that's something that has been done. As far as white dwarfs, I don't think anybody has really looked into that to see what it is. Yeah.
Question in the back.
Thank you for the talk. If we're interested in the dynamics of the massive stars, how important it is to take into account the gas component, and how does the gas affect the orbits of the star?
The gas, the ones that are not really getting into the hole, you mean? So the X-ray emitting gas has been seen, and in fact, this gas actually could be quite important also, because if you have any other gaseous material wants to come to the black hole, has to bypass, has to go through this the pressure due to the wind of these massive stars. So they do affect the environment also, because they have a high pressure gas, and it's X-ray emitting gas. X-rays have been seen here, but we don't really have the high resolution to see how they do it. And there's a lot of interesting things that can be done about the gas, how it's really affecting other stars. For example, there's a nuclear cluster sitting there. How do you have this X-ray gas that has a velocity of 1,000 kilometers per second, basically affects the atmosphere of some of these stars? These are all unknown questions that could be addressed also by studying them.
For example, for the S2 measurements, was it a thing that they took into account?
S2 is a sort of unusual. We don't really know if it has a mass loss. It really is difficult. We have not been able to detect the S2 star at any other wavelength than near IR. So this is one of the things that I really love to do, and I observed multiple times, and it's going fast, and it's hard to keep track of it. We have not been able to really see S2 star at radio high resolution, but definitely there are programs that try to really learn more about the S2 star and finding what the accretion, what the outflow rate is. If we measure that, that could actually be helpful because of feeding Sgr star.
You said a table with your estimation of
Yes,
magnetic
yes,
field.
yes, yes.
Yes,
I would like to know if you can also have a sort of, can you see the variation of magnetic field and its correlation with, for example, flux in infrared or
Yeah,
radio?
this is from the loop diagrams that I showed earlier, right? This is the
Yes.
one you're talking
Yes,
about,
yes.
yeah. Well, the magnetic field, really, we don't know that it's really very stochastic, so you really have very inhomogeneous. The magnetic field could be very different as you get in closer to the hole. So we're seeing the whole thing is variable. So as a result, it's natural to have a magnetic field that is changing constantly. And so it just becomes, these are all ruptures that are happening at different point. We don't really know how they are coming from, where they come from the accretion disk. And so I think it's not, I mean, the magnetic field just comes from the outer accretion disk, and then it just piles up and piles up. So I think it's very hard to really just see one magnetic field
So
sticks.
you cannot distinguish between various variation of magnetic field and other.
Yeah, we definitely see the magnetic field is different for every flare does it differently, because flares are sometimes bright, sometimes they're not, the time scale varies. So it's really very complex sort of series happen. One of the ideas is really to do is use gravity instrument to show where the flares are, and then observe also how flares are happening. So that would be really fantastic, because then you can measure the magnetic field at a given location in the disk of the black hole, and that'll be something really interesting to follow up in the future. Mhm.
The questions? Yeah, I have one.
Yes.
Do you have exactly retrieved the EHT period of these infrared flares that were going on, or don't you find anything that looks like that?
There is, in our power spectrum, we do not see anything that shows a periodicity.
Ah,
Is that what you're looking for?
yes, yes.
There is nothing that we can see as a
Fine.
periodicity. It's actually, if I show up by saying something like this, it becomes very controversial. No one has been able to really detect a periodicity that is confirmed. But one of the things that we're trying to do is observing for 24 hours. It gives us a lot more baseline to really see if the power spectrum shows something like this. But we just don't have the noise is still dominating, and if it's actually the periodicity is low, it'll be interesting. Really, everybody is predicting, because that allows you to measure the spin of the black hole. Because once you know exactly, so it's really critical to measure that, but our data doesn't show it yet.
Could you talk about the speed of the black hole? Could you sketch how you could infer it from flares? I don't understand.
Okay, flares are coming from the accretion disk of the black hole. The spin of the black hole is when we expect to see a jet coming from.
Okay.
So, but also it affects, if you have a spin of the black hole, then the gas can actually come closer, the accretion, the inner disk would be closer, so the flares could be closer in to the black hole, because the Schwarszchild radii is a function of the spin of the black hole. Then you have curved black hole, curved black hole.
The ISCO is function of the speed of
Yeah, that's right, yeah, that's right.
Most
Yeah,
different circular orbit.
that's right, yeah, it is, yeah.
Have you any hints of that?
We haven't been able to sort out these things, so definitely this is the spin is really, it could be know the mass well, we know there is no charge. But the spin is one of the challenges that I think I'm really excited that with these new instruments, maybe we'll find sometime this decade, I think, yeah. It's the key is to really observe this flaring event so that we can tell you a little bit about the variability and see if the periodicity is there and all of that, and then combined with gravity, we can find out basically where the flares are coming from. So it's really a lot, the future is actually quite bright to study this black hole.
Okay, so thank you very much. Farhad.